The strongest geomagnetic storm in 500 years in May 2024 began from a sunspot initially classified as completely normal. This active region, 3,664, rapidly expanded to 17 times the size of Earth, releasing coronal mass ejections directed straight toward us. This phenomenon generated widespread auroras across multiple regions, while also impacting observatories located deep underground. However, surface activity did not subside after the storm. On October 3, an X90 class flare, the strongest in 7 years, erupted directly at the center of the solar disk, triggering a G4 geomagnetic storm that disrupted radio communications. As measurement data confirmed the magnetic field had flipped polarity, NASA officially announced that the solar maximum of solar cycle 25 had arrived. How will this period of intense activity impact Earth in the coming months, and will it raise global average temperatures, causing the planet to warm up over the next year? To address these questions, analysing the operational mechanism of the central star is imperative. The Sun appears to be a stable and constant sphere of light, but actual measurements show that it is always fluctuating violently. Approximately every 11 years, this structure undergoes a major transformation process known as the solar cycle. This cycle establishes different physical states, directly affecting Earth in multiple distinct ways. The core factors changing simultaneously throughout the cycle include the overall activity level, magnetism, surface appearance, sunspot count, solar wind intensity, flare frequency, and coronal mass ejections into space. This operational law began to be recorded in the late 1700s through sunspot observation data. Astronomers of this era noticed a deviation from the assumption of randomness. Sunspots do not appear randomly. Their numbers increase and then decrease according to a pattern that repeats over time, with an estimated period of about 11 years. Initially, observers could only track the cycle by manually counting the sunspots that appeared on the surface. As measurement technology advanced, astrophysical models discovered two additional fundamental factors that also vary synchronously with this cycle: the solar magnetic field and its overall activity level. The mechanism of this transformation lies in the material structure of the star, which is a giant sphere of charged gas, or plasma. The shifting nature of plasma causes its magnetic field to constantly change. Measurements reveal that the solar magnetic field undergoes a complete polarity reversal in each cycle. This means that the solar magnetic north pole becomes the south pole, and the magnetic south pole becomes the north pole. This structural polarity reversal typically occurs around the solar maximum, identified as the midpoint milestone of a solar cycle. The polarity reversal drives the overall activity of the star to its highest threshold, causing phenomena such as the solar wind, solar flares, and coronal mass ejections to reach a dense concentration at the maximum before dropping to the lowest level upon reaching the solar minimum. The consequence of this magnetic polarity reversal mechanism explains why tracking the cycle today is no longer limited to mechanical sunspot counting. To construct accurate space weather forecasting models, scientists must simultaneously monitor 4 parameters: overall activity, magnetic field reversal, flare intensity, and the level of material ejection from the corona. Current data systems determine that humanity is presently in solar cycle 25. Prior to this, observation sequences had recorded and numbered a total of 24 solar cycles. Most of these cycles operate according to a familiar model, beginning with a phase of increasing sunspot numbers, reaching a peak of peak activity, and then gradually decreasing in number to return to a quiet solar minimum. However, historical data extraction sequences have recorded strange, non-standard periods where current physical models still cannot provide a complete explanation. The first deviation from the standard cycle model was recorded during the Maunder minimum, lasting from 1645 to 1715. Throughout this 70-year period, the Sun's sunspot generation mechanism nearly stagnated, causing them to disappear from the observable surface. Astronomers of this era collected data on only about 50 sunspots during the entire period, an extremely low parameter when compared to the regular pattern of thousands of sunspots appearing in a normal cycle. This severe decline in magnetic energy coincided with a period of climate change on Earth known as the Little Ice Age. Environmental data show that certain regions experience temperatures plunging far below average, leading to phenomena where rivers that rarely freeze, such as the River Thames in London, froze completely, suffocating Europe in severe winters. Immediately following the end of this period, another anomaly emerged under the name Dalton minimum, occurring from approximately 1790 to 1830. Although the intensity of the activity decline did not reach the extreme threshold of the Maunder minimum, the Sun's radiation and sunspot density parameters during this period remained much lower than the average value. This fluctuation continued to coincide with a global cooling cycle. However, mechanistic analyses indicate that the cooling did not stem solely from the quiescence of the central star. Geological data confirm that the temperature drop was also influenced by the consequences of large-scale volcanic eruptions, particularly the eruption of Mount Tambora in 1815. Ash from this event diffused into the atmosphere, which, combined with low solar radiation, directly constituted the phenomenon of the year without a summer in 1816. The direct causal consequence was widespread crop failures and a severe food shortage crisis spreading across Europe and North America. A more recent and practical demonstration of the instability of forecasting models is Solar Cycle 24, which began in 2008. Unlike previous linear calculations, this cycle operated in an exceptionally weak state, recording a sharp decline in sunspot numbers and overall activity compared to the system average, making it one of the weakest cycles in more than a century. Scientists faced a major deviation as the measured number of solar flares and coronal mass ejections were significantly fewer than simulated forecasts. This non-standard quiescence broke the continuity of previous cycles while raising core questions about the nature of the system. What factors truly govern the stark variation between solar cycles, and could a total decline period similar to the Maunder minimum recur in the future? The uncertainty in forecasting models continues to be clearly demonstrated as humanity enters Solar Cycle 25, which began in December 2019. Based on the weakening data of the immediately preceding cycle, scientists initially predicted that this cycle would continue to maintain a downward trend and be even weaker than Solar Cycle 24. However, actual measurements turned out completely to the contrary, as the activity of Solar Cycle 25 far exceeded all initial expectations and calculations. The severe deviation between the theoretical model and empirical data was marked in August 2024, when the measured daily average sunspot number potentially reached 299. This parameter was not only more than double the previously predicted value, but also established a level of activity never observed in over 20 years. In addition to the discrepancy in intensity, errors in the forecasting models also appeared on the timeline when the peak of the cycle arrived earlier than expected. At the time the cycle launched in December 2019, initial forecasting algorithms calculated that the maximum period would only occur in July 2025, with an estimated scale of about 115 sunspots. However, the actual rate of magnetic field increase forced NOAA's Space Weather Prediction Center to readjust the entire forecast in January 2024. This new simulation shifted the maximum timeframe earlier, falling between January and October 2024, while raising the estimated activity level to approximately 137 to 173 sunspots to match the actual rate of fluctuation. This calibration was reinforced on October 15, when NASA issued an official confirmation that the solar maximum period had begun. Nevertheless, an observational limit in astrophysics dictates that this declaration does not equate to the system having reached its absolute peak level of activity. Determining the precise peak of the solar maximum requires scientists to continue collecting data and monitoring surface activity for many months, or even years. Methodologically, the true peak of a cycle can only be confirmed with certainty after observation stations record a prolonged period of decline in energy parameters. Data extracted from the past 2 years has clearly reflected the star's high level of activity, with the frequent appearance of giant sunspots. Based on this density, scientists currently expect the Sun to remain in its maximum phase for about another year before gradually sliding into a quieter phase, the solar minimum. This means that Earth's measurements and defense systems will face heavy pressure in the coming months. The extension of the maximum phase indicates a high probability that the planet will continue to endure severe geomagnetic storms accompanied by spectacular auroral displays, while simultaneously increasing technical risks to modern technology systems and infrastructure. To fully understand the scale of technical risks that Solar Cycle 25 could cause during its maximum phase, analysing the historical data sequence of major solar storms that heavily impacted Earth is imperative. The most famous event, and also considered the strongest and most intense solar storm ever recorded, is the Carrington Event, which occurred on September 1 and 2, 1859. British astronomer Richard Carrington observed a giant solar flare on the surface of this star. Just a few hours later, a high-speed coronal mass ejection slammed straight into Earth's magnetic field, triggering an extremely powerful geomagnetic storm. The physical consequences of this phenomenon caused the telegraph system in Europe and North America to operate in complete chaos. Because the magnetic-induced current generated was too large, some telegraph operators received electric shocks when touching the equipment. Conversely, others noticed that telegraph machines continued to operate normally even when completely disconnected from battery power, as the induced current generated by the storm was strong enough to run the system. This geomagnetic storm also pushed the auroral belt far south to the Caribbean. The brightness of the night sky in these areas was so great that people could read newspapers outdoors. According to data from NOAA, gold miners in the Rocky Mountains woke up, proceeded to make coffee, bacon, and eggs, because this optical phenomenon led them to believe the sun had risen on a cloudy morning. This magnetic induction mechanism was further demonstrated by two telegraph operators on the Boston-Portland line who could maintain continuous communication for 2 hours without using batteries. During their exchange, their actual measurements also showed that the received signal was significantly clearer than when using a standard battery source. As society entered the next century, another major event recorded was the New York Railroad Storm in May 1921, identified as the strongest geomagnetic storm of the last century. At this time, humanity had not yet built a modern satellite system, but the storm still caused severe damage to ground-based electrical infrastructure. The powerful induced current caused a major fire at a station in Brewster, New York, while completely disrupting the railroad signal system across the northeastern United States. In August 1972, another powerful solar storm struck Earth and clearly revealed the environmental risks to space missions. This event occurred during the time interval between the Apollo 16 and Apollo 17 missions. Dose calculations show that if astronauts had been executing a mission in outer space at that exact time, they could have received a lethal radiation dose. On the ground, the intense magnetic field activity from this storm also triggered detonations of sea mines off the coast of Vietnam, as magnetic flux variations altered parameters and activated the integrated sensors within the mines. The vulnerability of modern power distribution systems was most clearly demonstrated in March 1989, when another violent solar storm struck the planet. In Quebec, Canada, the geomagnetic storm caused severe impacts to the modern electrical grid, triggering a large-scale blackout that left approximately 6 million people without power continuously for over 9 hours. The collapse of this network was severe enough to cause system voltage instability and physical damage to transformers across North America. This event served as technical proof of how vulnerable the modern power grid is to solar activity, thereby prompting engineers to design and implement new protective measures in energy systems worldwide. More recently, in early 2022, a solar flare, despite only having enough intensity to cause a standard geomagnetic storm, resulted in the consequence of 40 newly launched Starlink satellites losing orbit and being completely destroyed. In today's context, human society depends heavily on satellite networks and technologies that require a stable magnetic environment to operate. This dependence makes humans increasingly more vulnerable to periods of intense solar activity. A major disruption to this system could cause economic damage amounting to trillions of dollars, while posing direct risks to core infrastructures that modern life depends upon. Based on current economic models, an event with a magnitude equivalent to the Carrington Event occurring in modern times is estimated to cause damage ranging from 0.6 to 2.6 trillion in the United States market alone. In parallel with the technical risks to infrastructure systems and the economy, an important question is raised as to whether solar activity contributes to increasing Earth's temperature and causing global warming. In terms of radiation physics, during the solar maximum period, the total energy radiation reaching Earth does indeed record a slight growth. This increase in input energy has the potential to impact and cause some small fluctuations in Earth's climate system. However, meteorological models and convection measurements confirm that these fluctuations are relatively small, keeping their direct impact on global temperatures always limited within a narrow range. The causal relationship between these two factors is most clearly manifested through a chart comparing solar activity and Earth's temperature over many decades. The extracted data sequence indicates that until the end of the 20th century, the amount of solar energy received by Earth still strictly followed the natural 1-1-year cycle, as shown by regular, small up and down fluctuation bands. In particular, since the 1950s, the total amount of absorbed solar energy has not shown any distinct net upward trend on the long-term chart. While the solar energy curve flattens out, an important data discrepancy emerges as global temperatures record a sharp upward trend during that same period. The distinct divergence between these two data sequences proves the reality that the sun is not the primary cause of the global warming trend over the past half-century. Cross-referencing radiation measurements and surface temperatures helps narrow down the evaluation of the phenomenon. Solar maximum activity can constitute powerful fluctuations for space weather, but it completely lacks the physical conditions to explain the current global warming trend. Although solar radiation does not govern the global warming trend on the surface, the drift of charged particles during the maximum phase establishes harsh environmental limits for aerospace engineering. Intense solar activity can directly affect NASA space missions, including missions to the Moon. To control mission risk, operational guidelines are very clearly defined. Systems must avoid launching spacecraft near the occurrence of a solar storm. The mechanism of this safety standard stems from the fact that high-energy particles from solar storms are capable of penetrating protective shielding structures, posing a direct hazard to sensitive electronic equipment systems. When collisions occur, these particles alter the electrical charge state or cause short circuits in internal components. In addition to the risk of destroying hardware, they can also disrupt radio communications by perturbing the ionosphere and the signal transmission medium. In severe cases, attenuation and interference phenomena will make maintaining communication with the spacecraft extremely difficult or nearly impossible to execute. However, magnetospheric model analysis reveals a physical paradox where intense solar activity also has an unexpected positive side. During periods of violent solar activity, the magnetic field structure of this star expands and intensifies, creating a shielding capability for Earth and satellite systems against cosmic rays coming from outside the solar system. This means that high solar activity can provide an additional layer of dynamic protection against cosmic rays originating from peripheral space. Thanks to this particle stream deflection mechanism, satellite systems around the planet can be less vulnerable to long-term damage caused by high-energy particles from deep space. This increase in magnetic interaction leads to the observability of one of the most distinct optical phenomena during the solar maximum, the aurora. When a coronal mass ejection collides directly with Earth's magnetic field, it triggers a continuous sequence of electromagnetic fluctuations across a wide area. Initially, as the particle wave approaches, Earth's magnetic field operates as a shield to deflect most of the charged particles. However, a coupling mechanism occurs when Earth's magnetic field and the magnetic field of the solar storm connect directly with each other. This structural connection creates a tunnel that allows charged gas to flow down to Earth's dayside polar region, forming a rare dayside aurora. As pressure from the storm continues to increase, Earth's magnetic field lines are stretched sharply backward toward the night side like a rubber band. When the tension reaches its limit and snaps back, the entire mass of charged gas is driven rapidly along the magnetic field lines toward the nightside polar region, constituting the cause of brilliant nightside auroral displays. Spectroscopically, auroras typically display in the green color band, but measurements during periods of very intense magnetic fluctuations show that the sky can light up with an impressive red hue. This color separation mechanism depends entirely on two parameters: the type of interacting particle and the altitude where the particles collide with atmospheric components. The green aurora phenomenon occurs when solar particles collide directly with oxygen at an altitude of approximately 100 to 300 kilometers. Conversely, the rarer red auroral displays only appear when these particles interact with oxygen at a higher altitude layer, ranging from 300 to 400 kilometers. This difference establishes a naked eye observation limit for the red aurora variant. Red auroral bands, like the phenomenon witnessed in May, require an immense energy density, forcing them to be at least 10 times brighter than the green aurora for the human eye to perceive and observe clearly. The consequence of these magnetic force parameters determines the geographic map of optimal observation regions, including Canada, Alaska, Iceland, Norway, Sweden, Finland, Greenland, Tasmania, and the southern regions of New Zealand. During the solar maximum phase, due to the surging density and intensity of coronal mass ejections, the frequency and probability of auroral occurrences at lower latitudes, which rarely record this phenomenon, also increase correspondingly. This is one of the most visual manifestations, showing that Earth is interacting directly with a highly volatile Sunday. The visual link between the expansion of the auroral belt and magnetic flux fluctuations demonstrates that auroras are not merely a distant astronomical phenomenon. Instead, this increase in charged particle streams and magnetic field variations can directly affect ground-based technology systems, orbital satellite networks, grid stability, radio communication frequencies, and the safety of space missions. The entire sequence of events recorded in 2024 provides clear empirical evidence that solar cycle 25 is operating with an intensity far greater than the initial predicted parameters of simulation models. From this systemic deviation, upcoming geomagnetic storms during the peak phase could continue to pose serious technical risks to modern infrastructure that is inherently sensitive to induced currents. Simultaneously, atmospheric energy conflicts can also bring rare and brilliant auroral displays to the skies in regions that have historically seldom recorded this phenomenon. However, climate parameter analysis requires a clear data boundary line to be drawn. High-intensity solar activity is not the primary cause of global warming in recent decades. Long-term radiation measurements prove that since the 1950s, the total amount of solar energy hitting the planet has not shown a significant net upward trend, while thermal flow tracking stations have recorded a continuous, sharp rise in global temperatures. Therefore, the solar maximum establishes an important phenomenal state that must be closely monitored to control technical risks. But this data cannot be used to explain the modern global warming trend. In terms of environmental interaction, the current chaotic phase of activity serves as empirical data reminding humanity that Earth does not exist in isolation. Our planet always operates within a large-scale dynamic system, where the central star plays a dual role, serving as both a source of life-sustaining energy and a source of direct risk to technical infrastructure. The emergence of the solar maximum period therefore constitutes a real-world validation mechanism, providing a powerful reminder of humanity's position within a vast, volatile, and unexpected universe. Thank you for watching. See you next time.